Okay, so so all that is gone into in more detail on the video addendum from Monday's class. But I just want to point out that main point that going through a different independent variable, if you have the same surface, you got to keep the same ribbons. Okay, if it's the same surface that you're finding, it's the same ribbons, regardless of which variable you're using to generate. Okay, so we're going to move on to, like I said, physics applications here. And so we want to look at quantities of motion. Quantities of motion. And so here is the space shuttle. This was a NASA project from 20, 30 years ago. And this is a table that shows the velocity, I should actually say speed, the speed of the space shuttle every second after takeoff. And what do you notice about the speed? What do you notice about this profile of the speed of the shuttle as the shuttle's taking off?
It's increasing at a rate of 30 per second.
Okay, so good. So increasing at a rate of 30 per second. You see that every second the speed is going up by 30 meters per second. And that's a pretty close estimate. I think it's 29.8 or something, but just for simplicity's sake, I rounded it up to 30. But this is pretty accurate for this, what happens when these shuttles took off. So every second, speed is increasing by 30 meters per second. Okay, and so he said that was the rate. So let's go back here. So if that's it, so is 30 meters per second every second, is that the rate of change of speed? Is that the rate of change of speed? 30 meters per second every second? Okay, and you should be thinking yes, that's exactly what he said. It's the rate of change of speed. Okay, and so as a test of whether we've learned about rate of change in this class, a deep meaning for rate of change. What is a deep meaning or a fullest meaning of rate of change? If the rate of change is 30 meters per second, how could we frame that value to get the fullest and broadest meaning of this rate of change? Anyone?
May I attempt it?
Please. Yep.
Okay, so for every variation in speed, that variation comes from the rate of change times every variation in x, which would be seconds in this case.
Okay. All right. So he talked about a variation in seconds. Does that variation in seconds have to be 1 second?
No.
No, right? So how much does the speed go up in half a second?
30 times 0.5.
No. How much does the speed increase in 1/2 of a second?
15 meters.
15 meters per second, right? And how much does the speed go up in 1/10 of a second? 3 meters per second, right? So the fact that the rate of change is 30 meters per second tells you a lot more than just this. And this is a theme that we've repeated over and over in this class. But past experience shows me that by this point in the class, there's still hasn't taken hold fully yet. So we'll just review it again. So this rate of change tells us a lot more than just every second the speed goes up 30. It also tells us how much the speed goes up in 1/2 a second, and in 1/10 a second, and in 1/100th of a second, and in 3/4 of a second. Okay, so given any variation in time, dx, what can we say? how much does the speed increase during a variation in time of dx?
The speed increases by 30 times as much as the variation.
Good. You just take whatever variation, so say a tenth of a second. To get the variation in speed, you take a tenth of a second times the 30, or 3. In 2 seconds, you'll take 2 times 30. So given any variation in time, the variation in speed, I'm saying velocity, so I say dv for velocity, is 30 times the change in time. So that's what we mean by that the rate of change of speed is 30 meters per second per second. Okay, so if that's the case, then let's predict the velocity at 4.7 seconds after takeoff. And I just have one restriction. You can't use a dx of 4.7. That's off limits. Okay, so don't use a dx of 4.7. So I want to know, predict the speed at 4.7 seconds after takeoff, and we want to apply what we're just talking about, but don't use a dx of 4.7. Okay, so we want to stick to dx being small variations in x. Okay, so how would I do that? So how can I use our meaning for rate of change to predict the velocity at 4.7 seconds after takeoff? Somebody new?
I think you could just multiply 30 by 0.7 and then add the 120 that was at 4.
Okay, so you're saying you want dx to be what?
0.7.
So we want to see a small variation in time of 0.7 seconds. And then we know how much the speed will go up. How much does the speed go up in that variation of time?
By 21 meters.
Yeah, so 30 times 0.7, or mdx, right? And that's the 21. Okay, so from 4 to 4.7, we get an increase of 21 meters per second. And therefore, the speed at 4.7 is?
141 meters per second.
And how'd you get that 141?
You add 120 to the 21.
So take the speed that it was at 4, and then 0.7 seconds later, we know that in that 0.7 seconds, the speed goes up by 21 according to mdx. And so we add the 120 plus the 30 times 0.7, or 21, and we get the 141. Okay, does this structure look familiar? What does the structure look like?
Where we would add up all the changes in the current interval.
Okay, so what's the 120 then?
That's the meters per second in the given 4-second interval.
Right? Yeah, so it's like the previous
exact total accumulation.
Exactly. So this is the form. Is our previous accumulation plus?
Accumulation in the current interval.
Yeah, so this is all the previously accumulated changes in speed. This has accumulated up to 120 meters per second. And now we're adding on a little bit more. So, let me erase here. So we could write that as So really, in terms of a accumulation function, or a speed function here, what's really kind of just a very easy way to generate any speed at any time here. Because at 0 seconds we have 0 meters per second, we could really write kind of an easy formula here to generate the speed at any time, including 4.7. So what would that formula be? What do we do to x to get the speed?
30 times dx.
Okay, so now I'm talking not about dx, but just about the time since takeoff. X is the time since takeoff. So
What is the
X final minus X initial, and then that times, because that's still dx in a way.
Okay, so are you saying this? Like that? That's our.
In that, yes, I mean that makes sense in that current interval of at 4 seconds, because
Okay.
we're adding 120, which is the meters per second.
Right, so like times for times after. And actually it works for times before too. If your x is 2, you actually take away 2 of times 30, and it still works even for times before 4.
So we don't need to replace 4 with the X initial value or so?
Well, we're using 120 as our initial kind of reference point in the way we're writing it here.
I see.
And so you can actually put in x values less than 4, and you still generate the right speed for those x values. Because you'll get a negative, say, if x is 1, you get negative 3 times 30 is negative 30, negative 90, plus 120 gives you the 30 at 1 second. Okay. So now I want to write this. I want to write this as how can I rewrite this equation incorporating integral? So how can I, so like our total accumulation function, right? So how can I write this function again with our total accumulation generic form? What would it be? So it still has the same structure, right? Be 120.
Okay, I'm just going to try 120 plus and then the integral.
Yeah.
And so in this case, we're going to go from 4x to 4. Oh, sorry, 4 to x.
4 to x.
Yes, on the top.
Okay.
And then we're going to have our RF, which is basically 30.
Good.
Yep.
Is that the end? Just 30?
No, we should have dt.
Yeah, good.
Yeah.
Very good. Okay, so these both achieve the same thing, but they're of different forms, and that's what I want to talk about now. This form, what? It calculates, it generates values of x, or values of speed very easily, readily. You know, it just cranks out lots of speeds with an easy computation. This reflects process. It reflects the fact that we are accumulating speed bit by bit, right? This is the sum of little changes in speed, right? 30 times dt represents one small change in speed. And then we're going to accumulate those starting from 4 to x. This doesn't spit out values of speed very easily. So we want to focus on the fact that there are two different forms here that are doing the same, showing they're the same function, but in two different forms. And so this first one is called closed form. What's the deal with closed form? Closed form is made up of operations and functions that are familiar and that generate values quickly. So closed form involves plus, minus, times our common operations, and then polynomials, sine functions, exponential, logarithmic. Okay, so any of our familiar functions that you could just go to a calculator and then it could give rapid fire results, right? You just x is in, y's out, x is in, y's out, and you can just generate numbers all day long. So they're really efficient at computing values of the dependent variable. So again, any combinations of our operations, polynomials, sine and cosine, exponential, logs, all are familiar functions, and all the combinations of them. Okay, that's called closed form. Okay, open form, on the other hand, so that's closed form. Open form means that reflects process and meaning. Where do we get? Where does this final speed come from? This 141. It came from the fact that we knew the speed was 120 before, and then that 141 came about as the shuttle sped up bit by bit, right? The shuttle went faster and faster bit by bit, and we summed up all those bits of change to get the total net accumulation of changes in speed, and then added it to the 120. So it's reflecting the process, right? We're summing up bits of change. Okay, but this form. So how are we able to get values of this function when they're in this form? How did we get values so far? How have we gotten values of a function like this in this form? GC. We had to go to technology, right? We had to put it into GC and and use function notation to crank out values of, in this case, speed, or the dependent variable. We can't do it by hand readily because there's too many things to add up. It's like adding up a zillion little changes in speed. Okay, so where the open form, open form, it reflects the process and the meaning, but does not compute values conveniently or quickly. All right, so they each have their advantage. They each have their advantage and their strength. Closed form, its strength is rapid fire results. We can get lots of values of the dependent variable quickly because we have familiar functions, an easy expression to calculate. Okay, that's the advantage to that. The advantage to open form is it reflects that meaning and that process. We know what we're looking at here. It's like, oh, speed is going up bit by bit, and we're summing up all those bits of changes in speed to get the final speed. Okay, does it make sense? Does it make sense, the difference between open and closed form?
Yeah, so just to clarify,
Sure.
The integral equation that we have,
Mm-hmm.
that is an example of open form.
Yeah,
like
this is the part of this function that makes it open form, right? So our net accumulation functions, when we write those integral net accumulation functions, those have always been open form expressions. So I kind of cut you off. Was that your whole question?
No, yeah, it was.
Okay. All right. Very good.
So is the one above integral closed form then?
Yeah.
The one with the x minus 4?
Right.
Okay.
That's closed form. It involves basic arithmetic and familiar functions. It easily computes values. Open form involves something that demonstrates process or meaning, but is not helpful for getting lots of results fast, right? It doesn't compute easily. We need GC to give us values like this, using kind of some numerical methods, right? Some like computer methods to come up with values of the function. Okay, other questions, clarifications? Okay, so just in summary here, We say changes in velocity are accumulating by 30 meters per second each second, and that's called acceleration, right? So acceleration, how does it relate to velocity? Acceleration is?
It's like if the speed is speeding
The rate
up.
of change.
Yeah, if the speed is speeding up, that's right. If the speed is speeding up, and that's, someone else has said, that's the rate of change. It's how much the speed changes, so it's the rate of change of speed. And in this case, for this example, we assumed constant rate of change. We assumed it was a constant at 30 meters per second, but doesn't have to be true. There's, in fact, probably a more realistic model of this would have actually a changing rate. Okay, it would have some kind of changing rate. Go ahead.
Info? Or would we need info to find the acceleration?
Sorry, you're breaking up there. Can we try again?
Do you need more info for acceleration in this problem? Or can we find it based off the given?
We assumed, given here, we just assumed it was constant at 30 meters per second per second. But if you wanted a more realistic model for the acceleration of this rocket, blasting off, yes, you would need more info.
Got it, thank you.
Yeah, sure. Okay, so let's do an example where we have actual changing rate of change, right? So acceleration is changing. Let's look at that. So I have this situation here. Here are two cars, and I have acceleration functions. Car 1 is the blue car, and its acceleration function is this one here. And car 2 is the red graph, and its acceleration function is here. Are these acceleration functions given in open form or closed form?
Close.
People are saying closed. People are saying closed. And that's right. We've got just operations and familiar operations and functions. These functions will generate values quickly. They'll give us rapid fire results. At 1 second, the acceleration is such and such. At 1.1, at 1.3, we can rapid fire get, like imagine if you had a handheld. You could use a handheld calculator to generate values of acceleration pretty quickly. Okay, so a couple questions here. Which car is moving faster at 2.5 seconds? Let's take a look here. Here's 2.5 seconds. So car 1 is this wavy blue curve. Car 2 is the smoother red curve. And here's 2.5 seconds. So which car is moving faster at 2.5 seconds?
Car 2.
Okay, someone said car 2. And you're seeing that this...
Car 1.
So I'm assuming the answer for car 2 is because its y value on its graph is higher than the y value on the graph of car 1. I would assume that was how you made that conclusion. But then someone said car 1. And so why car 1?
Because at the start it has a higher, the graph goes higher, really quickly compared to car 2. Car 2 is like a slower increase in graph. So car 1 would be faster compared to car 2 at 2.5.
Right. So we know that our velocity. So these t here. What is the net accumulation, say, from 0 to t of our rate of change, which is acceleration. So we have to look at, we can't just look at these. This is the current acceleration of car 1 and car 2. So car 2 is accelerating. Its speed is going up faster than car 1 is. But in terms of their current speeds, we have to look at what's happened before, right? We have to look at the accumulation in changes in speed. So we think about breaking this up into intervals. And we know that each accumulation in speed we can find by how? Each accumulation, a little change in speed, is found how?
The rate of change times the change in time.
Good. Right? So what's happening here? Our rate of change, our acceleration here is much higher. So we've got the same change in time all the way through here. And so look at these values of acceleration. They're much higher than these values of acceleration. And so if we're accumulating these changes, it would be what? Acceleration times change in time. Acceleration times change in time. Acceleration times change in time. And so those changes in speed will be much greater for car 1 than car 2 in the first, whatever seconds here. So here's where the acceleration change the accelerations are the same, and it swaps. But if you imagine that you're accumulating changes in speed, each one is the acceleration times the change in time. So if you're accumulating, for summing up, the acceleration, the rate of change, times changes in time, by the time we get here, which car has accumulated more, a greater amount of changes in speed? Clearly car 1, because of its acceleration values were much higher through there than the acceleration values of car 2. Now, it changes, right? Starting at this time, it changes, and now the changes of car 2 in speed are greater than the changes in car 1, but not enough to overcome the damage that was done, right? So in this first part, car 1 gained a big lead in speed. Car 2 is now gaining some of that back, but not enough by 2.5 to overtake the accumulation of changes in speed that car 1 had in this first part. So we definitely say that at 2.5, car 1 is going faster. Does that make sense? Any questions on that? All right, so using that same kind of reasoning, when will the cars have the same speed for the first time? When do you suppose they'll have the same speed for the first time? How about,
Probably at about 7.
How about here? What would you say here? Which car is going faster at around 3.2 seconds?
It's still car 1.
Still car 1, because these differences in acceleration are a lot greater than these. So probably still car 1 is going faster. And then in this next part, car 1's acceleration is greater again. So now here car 1 is still going faster. It has the increased velocity from this part plus the increased velocity from this part, and then not enough compensation. So somewhere, where? Someone said 6 or 7. Does that seem reasonable? Somewhere around here, the speeds are going to be the same for the first time. Car 2 is finally going to catch up in terms of speed. It's going to get up to car 1's speed. How can I know for sure? I want to know exactly the time that this happens. What should I do to find out exactly when car 2 and the two cars have the same speed for the first time?
graph the total accumulation.
Okay, total accumulation, or what function do you want to graph?
The total accumulation, like the integral of the rate, like integral and the rate of change.
Good, yeah, so we want to develop the speed functions, right? So if we want to know when the car's speeds are the same for the first time, we want to write down the speed function. So, and I kind of did that right here. So for car 1, say V1, we're going to write the integral from 0 to t of its acceleration. And then for V2, we want to write its own accumulation function for its speed, or sorry, its acceleration, right? Its acceleration function, which is the rate of change of speed. Okay, so let's do that. I think I already did that. Let's take a look. So here's the velocity functions. Now I'm using our new notation, a and t, and then v2, a and t. And so these velocity equations, are these given in closed form or open form?
Open.
This is our open form, right? This is our open form. Okay, so now I want to know when they going the same speed for the first time. So how can I figure out when the two cars are going the same speed for the first time? What should I do?
Set the two equal to one another.
Okay, set them equal to one another. I'm going to set these equal. And do what? I'm set them equal and do what?
Well, you want to solve for time.
Okay, what about that? So I'm going to set these integrals equal, and I'm going to solve for time. How about that?
Yeah, you have two unknown. Never mind, I forgot. Because you have the starting and the end.
Oh no, it'll be 0,
okay.
Right? They both start at 0. They both start at 0.
Oh, okay.
Okay, so?
Sorry, yeah, then that should work.
That should work.
Then you just, yeah.
What do we think about that? Is that?
I'm sorry to interrupt, but my thought process was if they're open form, like you said, and not easily computed, wouldn't it just be easier to graph and see where they intersect?
That's the point. Setting these equal and solving for t, that's right in theory, but what is the big obstacle here? Open form. Open form are, they're expressions that are not easily computable. And now we've got two of them and we're setting them equal, right? We got different rate functions locked inside these integrals. Okay, so this is, by the nature of open form, this process, setting them equal and solving for t, is difficult, not easy, not efficient. Okay? So some people have been saying, let's graph them, and that's the way to go here. So let's let GC graph these functions, and that's the way to really find out when they're going to have the same speed for the first time. But just underscoring that, look at this problem that open form is presenting to us. We have the right procedure to get this, set them equal and solve for t, but open form is like, no way. The door is, it shuts the door in our face. You ain't coming through here, right? You're not going to solve this and get t very easily. Okay? So let's graph it. So I'm going to graph them both. So we put what car 1 was blue. And I'm showing this in the right-hand pane using the apostrophe, right? So apostrophe on y and x will open up a second window pane and graph it in the second window pane. And so where is the speed the same for the first time? Or when, I should say. When is the speed the same for the first time?
It looks like 6 seconds around there.
Okay, I'm going to zoom in. Make sure I got the right point there. Looks like I'm locked pretty much on it, and we're at Is that 5.6 something?
5.625.
Oh, up here, right. Sorry. Yeah, use it. 5.625. So that's when their speeds. So car, right, we said in terms of speed, car was behind in speed, and car 2, and then caught up. So we said we thought somewhere around 6. And in fact, it's 5.625. And then the speed at that time, that when they're the same for the first time, is this y value 11.878.